Hello all, welcome. My name is Bulent Tasdelen. I am working as Business Development Manager at Kisser Group. I'm going to talk today about data acquisition and how to interpret your results while making cutting force analysis and measurements. I hope that at the end of the webinar you will be able to improve your measurement chain and also get some hints about how to interpret the results. Let's start. I have divided the presentation into mainly two topics. Data acquisition, I will start with that, and then we will go and look to how we can interpret the results by giving some cases where and references. Let's start with the data acquisition. And we will start with the choosing the right measurement range, and it depends on certain things. In the second chapter, I will introduce the effect of alliance, how to utilize alliance filter or correct low pass filter to avoid the alliance, and then at the end talk a little bit about how to choose the sampling rate. Let's start with the first topic. How we can choose the right measurement range, and that depends on two things. The first thing we should consider is that before we start to set up our system, what are the specific frequencies to capture during cutting force measurements, right? So depending on milling, grinding, or turning, we are working with different machine dynamics and process dynamics. So we have the rotational per minute of the workpieces, RPM of workpieces. You have the RPM of the tools. You have the later on the cutting edge passing frequency. So imagine you have a tool, a milling tool, you have 4 cutting edges. You have a certain RPM, so your cutting edge passing frequency is then, at this specific case, 4 times your RPM, right? Chip formation frequency, how often the chip occurs. So there are different ways, of course, to calculate this. You can collect chips and measure the length, and since you know the cutting speed and the speed of the chip can be calculated from that, then you can calculate the chip formation frequency. Or you can also look to the contact lengths on your chip side, then you know the length of the contact for each chip, then you can also calculate the chip formation frequency. Lamel building, so lamels are the deformation bands that occurs in the shear plane, and it's of course being affected by the type of the material, the process data, the coolants that we are using, and so on. So that is also a way to understand the process and to understand the machinability of that material and why certain types of wear occurs in our tools. Any microstructural properties can be captured. I will give some examples from a researcher that has managed to see certain constituents of the microstructure. Chatters, of course, cutting forces consist of also of course the effects from any vibration coming from the machine or the spindle or the linear moving axis or the process excited and so on. So that effect can be also captured in cutting force measurements. Resonance of the machine parts can come from your machine constructional parts like bolt screws, spindles, tables, gear systems that you have in our spindles. Any disturbances that may come from external equipments, especially from coolant pumps. And of course, also when you start analyzing and if you have certain conditions and certain signature of the process and machine, you can still capture part of those properties in your cutting force measurement. So when we know which kind of frequencies am I expecting in my process to make the measurement on, now it is time to have a look if we can measure those frequencies with the measurement chain that we have. And the first step, as I said before, we need to check the product information of the hardware and software. is if there is limitations when it comes to the maximum frequencies. And the second step is to have a look what is the natural frequency of the sensor itself when integrated in the structure, because that will be a limitation factor. If you have a look on the frequency response function of a sensor system, in this case one of our dynamometers, you can see here that there is a distinct spike at certain frequencies, and that is what we call the natural frequency of that sensor itself. So you can see that there is a phase shift. So, and if we make the presentation of this as a general rule, you can see that frequency response function. So you have frequencies in x-axis, you have the magnitude of that system. You can see this distinct spike at certain frequency, that what we call natural frequency f0. And what we say is that the maximum frequency that you can capture with such a system having a natural frequency of f0 here, it's somewhere between 1/5 and 1/3 of this natural frequency. And of course, later on, let us say in this case, the maximum frequency that you can capture with such a system is 1/3 of it. This is where you put your low pass filter. How to find out the natural frequencies of the dynamometers, for instance? You can do in different ways. If you have an accelerometer, then you can place that on if it's milling or grinding, turning, doesn't matter where the chip will occur. Yeah, close to that point, and then excite the system. Yeah, and you can do it in different ways. You can simply make a gentle hit on the dynamometer with an Allen key. So you can use the dynamometer itself also to calculate or to measure the natural frequency with an Allen key, as I said, or a plastic hammer, and you are making the measurement in the time domain, as you can see here. So later on, you need to transform this measurement into the frequency domain, and you can also do that with our DynaWare software. As you can see here, now we have converted this, so we have certain frequencies, the natural frequencies of the system, represented here with the red areas here. So this means that our system has a natural frequency at that frequency, as you can see here. And of course, this is also indicating that if you are using certain RPMs and certain tool path passing frequencies and so on, you should avoid to be close to those frequencies. Otherwise, you will excite that and you will be measuring that. So after talking a little bit about some limitations that can come from the hardware or software or the dynamometer in this case as presented, or the sensor itself, let's look to the alliance, how to avoid and how to set up at the right filtering strategy. Let's start by explaining a little bit about data acquisition. As you can see here, a physical happening in a true signal is as you can see, it's in a sinus form. You can see those rectangular meshes here, you see here, and the horizontal resolution is actually the time difference, the time passes between each sampling. Yeah, so we are trying to make a sampling, and the time passes is this horizontal part of the rectangular. The vertical part, the vertical resolution, is the bit width. Yeah, and those are properties of your data acquisition system or your AD conversion. Yeah, so sampling rate, it can be presented as sample per second or also hertz. Yeah, but it is a properties of how fast you are sampling. For instance, if you now we start looking to the difference between higher and lower bits, as you can see here, and frequency happening in a sinus form. If you have a 14-bit, you have this red curve here. But if you have a 3-bit, as you can see, the vertical resolution is lower. That it will cause steps, so your accuracy will not be as good as the 14-bit. If you now talk about the sampling interval, as I said before, the sampling interval is the time that passes between two sampling points, and the inversion of it, of course, the frequency, the sampling frequency. As you can see here, the red curve is the true signal, and the blue dots are my sampling. So if you, of course, if you improve the amount of the blue dots here, then you will get a better resolution also. Let's look to this example. Again, a sinus wave here that occurs at 100 Hertz. Yeah, this blue vertical line here. And we are sampling with 1000 sample per second. So 1000 Hertz. This means 10 times. So we are up here. So this means that one true complete signal will consist of 10 sampling points. And this is what you can see here. So we have 10 of them. It means that the stored signal will be correct. So we are sampling 10 times of the true happening here. So we have the right capture representation of that the true signal. If you look to this example, then we have 900 Hertz instead. Yeah, and we are sampling only with 1000 sample per second, so 1000 Hertz. So if you look here, we have 900 Hertz, and then we are sampling with 1000. So it's very close to that. So it means that we will have, as you can see here, 10 times happening in this representation here, and this means that the signal, the stored signal, will be much different compared to the true signal. And what we are actually measuring here is the difference between, as you can see, the true signal and my sampling rate. So 1000 minus 900, 100 Hertz. So now we are measuring 100 Hertz only. So that's why we need to apply at least the Nyquist-Shannon sampling theorem, and it says that the sampling frequency has to be at least 2 times the maximum frequency that you want to measure. That's what Nyquist-Shannon says. Otherwise, you will have an aliasing, so you will measure false frequencies, and I will explain this. So it means that if you have a true signal that you want to measure, your sampling rate should be at least 2 times bigger than that. So you should not be, your maximum frequency range should not be in this red region here. If you are there, then you will be measuring the difference between the true signal and your sampling rate, as you can see here, because you don't fulfill the Nyquist condition. As I said before, what you're going to measure is the difference between the true signal and the sampling frequency, if you don't fulfill the Nyquist condition. So let's have a look to this system, as you can see here. This is a true happening in one of our machining operation. We have certain frequencies, as you can see, 25, 70, 160, and 510, and maybe some frequencies between. And what we do is that we choose a sampling frequency that is 100. Yeah. So what will happen is that since we have the sampling rate 100 Hertz, which is not really high enough, you remember the maximum frequency that is here is 510, and we need to have at least 2 times, but we are at 100. So what we will be measuring is for instance, the difference between 170 as a 30, as you can see here, 30 Hertz here. We will be measuring, you can see there's another frequency, 160 here. So the second harmonic of sampling frequency rate 100 is 200. So we will be measuring 200 minus 160, 40, and the same 500, and the difference between 500 and the 510, and that is 10 Hertz. So we have those aliasing terms coming in since we have a sampling frequency which is high enough, and we will be measuring those frequencies which are actually false frequencies. Let's look to this system where, as you can see on the left hand side, how we can avoid anti-aliasing with the anti-aliasing filter. As you can see here, we have a sensor system, then later on we have a signal conditioner, and then we have a data acquisition, and then we may have post-processing analysis. So, and we have some true happenings, physical things that happens at certain frequencies represented with blue lines here. And then we are actually interested in this frequency range, as you can see here. We have a bandwidth of the conditioner, which is going up to higher frequencies. Yeah. So on the left-hand side, we don't use any filtering. On the right-hand side, we are using a low-pass filter because we say that we are interested in this region. So we put a low-pass filter, and that will act as an anti-aliasing. Yeah. So we are not getting the higher frequencies in this case. And then we choose a sampling rate, as you can see here. The same thing on the right-hand side, sampling frequency here. On the right-hand side, since we have used a low-pass filter during signal conditioning, and that sampling rate is at least 2 times bigger than what we are measuring, then we will have an alias-free data. But as explained before, in this left-hand side, since we have not used any filter, and we don't have any anti-aliasing filter either in our data acquisition system, what we will be measuring are the false frequencies. And some researchers make filtering after acquiring the data, but it will be too late because even if you put your low-pass filter where you are interested in, you will still be seeing those false frequencies that are actually not existing in your system. So one way was low-pass filter, like we have on the right-hand side, to avoid aliasing, and the other way is, of course, to have anti-aliasing filters. Some of the data acquisition systems, they have automatic anti-aliasing filters, and with the help of that, then you will be measuring the right frequency. So then if you look to our, for instance, DynaWare, when we are setting up with the LabM, in this case, we have 8 channels that you can see. We will label them after what is set in our datasheet for a specific dynamometer, 8 channels. Later on, we also look to the calibration sheet. We need to put the sensitivity and the measurement range that we are interested in, yeah, for each channels. And then later on, as I said before, we need to use the filter, the low pass filter, already while we are acquiring the data in this case. Yeah, otherwise we will have an aliasing effect. The time constant for quasi-static measurements, which cutting force is long, so you need to choose long. So now we talk about a little bit data acquisition. I hope that it will help you to improve your settings. And now the main question arises often: how to interpret our data. And of course, this depends a lot on which kind of operation you are using, what kind of machines you have, how much energy and time you have put and knowledge you have about your machines. That I explained in the milling and turning webinar, that, for instance, with a simple accelerometer, you can go and measure what kind of frequencies are coming from different parts, like linear moving heads and spindles and coolant pumps and so on. When you put them all together, it will be much easier, of course, to interpret your data, which will be still specific, but I will try to give some examples, and hopefully those examples can help in your case also. If you look to a cutting force measurement, so regardless of if it's turning, milling, or grinding, or even drilling, you have different force components. Let us, in this case, look to 3 force components. We have feed force, passive force, cutting force. As you can see here, we have static part of the force measurement. So in this case, it seems to be quite constant, but with the tool where we know that it can have tops and valleys, it can have some slopes going up and going down and so on. Yeah, but that is the static part of the force component. Then we have a dynamic part. Yeah. And later on, of course, then we also have the ratios between the force components. So if you are working with understanding and making research on cutting forces, you need to consider and look to those 3 properties of a cutting force measurement. The force signal consists of the information from chip, how chip formation occurs, tool wear and tool wear type, surface quality that depends, yeah, dimension and roughness. So if you can especially find the correlation between the dynamic part, for instance, and the surface roughness, you can use also a force measurement to some sort of make an indirect control of your quality, yeah, which can be used in R&D to build models and correlations, but even in production, you can use that knowledge when you know that correlation to a certain part quality parameter, then you can use it as an indirect quality measurement, and thus decrease the amount of quality measurements that you are spending in your operation. Of course, if you have some imbalances of the spindle and workpiece systems, you will have different dynamic part. If you have interrupted cuts, which I will also show one case, you will see that in both static and dynamic part. If you have out of roundness and workpiece, that is a little bit affecting also. It will cause an imbalance and also high dynamic. Microstructural effect, I will show an example from a researcher from UK where you could see the different effect of the different part of the microstructure in the force measurement. Of course, as I said before this slide, that if you have certain properties of your machine, mechanical and electrical configuration, like stiffness and damping, which affect the deflection of your system, you will see that effect also on your cutting force measurement. And also, sometimes when you have external forces, that is also affecting, like coolants and oscillations from external equipment, such as pumps and robots and so on. Let's look to this example. It is from Mehdi Aynian here and Professor Yusuf Altuntaş, where they work with the chatter stability in milling. Some of you are familiar with such plots. They are called stability loops, where you have the force, and that is represented often with depth of cut or feeds. And then you have frequency domain, where you have spindle speeds, rotational speeds, and so on. So you have some stability loops, meaning that below this red curve, you have stable process, but over that curve, you have unstable. So then if you look to this part here, the force measurement, when you are measuring when forces while making the machining operation at certain cutting condition, you will have stable conditions. So you will have a typical noise level or dynamic, so to say, in milling. But if you are in the unstable regions, then you will have you will see the chatter. So then, of course, you have a wide spectra of the representations between these two. So this means that when you look to a force measurement, you also see the indications of oscillations starting up or heavy oscillations. Yeah. So noise of your or the dynamic part of your force measurement can give hints about the chatter and oscillations and so on. Then let's talk about a little bit stiffness and deflection, and I will give an example how to correlate force measurement to actually deflection, both dynamic and static deflection. Let's start with this example. You have an CNC machine or robot. As you can see, we have you have a drive with scales that run this according to your coordinates and feeds that you have a program. You have different type of interfaces here. You have your tool here, cutting tool. It can be turning tool. It can be milling tool. It can be drilling. It can be a grinding wheel. It can be a honing stone. Doesn't matter. You have different type of interfaces, and of course, this is a mechanical structure. We did not. It's not an infinite stiffness. So this means that you are deflecting, and the more joints you have, of course, the more deflection that you will have in your total deflection. So when you have cutting forces in 3 directions, you will have a delta D deflection in also 3 directions, right? And these deflections, they will cause alterations. So it means that if the tool is being deflected from the center to this inclined line here, this means that you are not really following the coordinates that you have programmed for. So it will affect your surface because of the deflections. So a way to measure the deflections is actually to be able to know and measure the stiffness of your system, and that you can do with the help of a force and displacement sensor. So if you are measuring force in some sort of like a setup step before you make the machining, if you place a displacement sensor on the other side while you are pushing against your workpiece or your grinding wheel and measuring the force, then you will be plotting the force versus deflection. And the inclination, the slope, is actually the stiffness of your system. So then you know your system, how much it deflects for each Newton. Yeah, how many micron it deflects. And of course, this means that later on, while later on you are making the machining operation, you have cutting forces. Those cutting forces, if you look to that measurement, you are actually, if you multiply that signal with the stiffness value, yeah, so the inversion of 1 over stiffness, if you multiply it with the force, you are actually looking to the deflection. Yeah, so this is a way to measure the deflection, and that is of course affecting your surface properties. And that is being used and represented in this patent, an old patent. If you look to the force measurement here, as you can see, it's a force in Newton during the time scale. And when you take this part in turning operation and measure the straightness, how straight you are cutting, that is called profile accuracy, you can see that they are resembling a lot. And that is because the turning tool, because of the force, is being deflected outwards in this case, and that will also leave imperfections on your surface. And in this case, the owner of this patents, they have used this in order to improve the straightness, the profile accuracy. So they connect the force signal to the machine. As you can see here, when they have the force control during chip formation, they are changing different settings of the cutting speeds and feeds and so on. They are cutting much straighter compared to not having force control, where you have the effect of the deflection because you have some different depth of cuts due to the imperfections coming from the pre-operation. Yeah. So as you can see, when you look to especially the statical part of your force during turning operation, for instance, or during creep grinding, for instance, yeah, then you will see that there is an effect of the deflection on your part. Let's look to a milling tool now. In this case, face milling, we have 4 inserts, and yeah, we look to a torque measurement. If you can zoom to that measurement, you will see that you can really see the moment distribution around each insert. Yeah, and that can also be seen with the polar diagram. Yeah, by utilizing our software DynaWare, for instance, you can see the torque level on each edge, and that is also, as you can see, thanks to this dynamic part of the measurement with the piezo technology, you can really see the moment on each insert. Yeah. And by analyzing these, then you can get ideas about if any unbalance wear occurs on one of the inserts, or if you have any big run out on your tool, and so on. Yeah. Another example is from Suarez Fernandez here, a work done in UK, where while doing the face turning, cutting forces are measured, as you can see here, and in order to find the start and exit of each rotation, a slot was made here. So cutting forces are measured, and afterwards the surface is also etched, and the material, the microstructure, is analyzed. And if you look to the force measurement, the dynamic part of the each measurement is, you can see those small spikes because of the slots. So you have one rotation. These researchers, they have put those rotations in an as you can see, as a round representation, but by putting them one another after each other, and then analyzing the dynamic part in as you can see, with different colors, topographical representation, they can see the correlation of the forces and the microstructure, certain grains that they have in the microstructure. Yeah, so this dynamic part of your system, of course, depends on the material that you are measuring, yeah, you are machining. Bar formation and forces in drilling operations, it's often being researched on. As you can see, these plots, they are force measurements done with a dynamometer here, and where you measure the forces and the moment. As you can see here, and this work is being done by Mehdi Aynian here, and as you can see here, when the wear is low, at the exit of the force level, you have certain noise, certain dynamic. When the wear goes up, this level goes also up, and that is because you have this correlation between the noise level and the bar formation in drilling operation. Another part is from turning, where if you are working with, for instance, evaluating, in this case, different phenomena in chip contact, like contact length and chip upcurling, or you would like to see the effect of any coolant or lubricants, for instance. In this case, and the turning operation started dry, and in the middle, the MQL, minimum quantity lubrication, which is applied externally to the insert, has been switched on while measuring the cutting forces. And you can see that there is a slight effect because of this MQL. And that is also being seen in the chip formation. So if you look to the chip upcurling radius, you have a little bit smaller radius with the MQL compared to dry operation. So what you are doing is that you are, when you look to that small difference in the forces, it is indicating any difference in chip upcurling and contact length in this case. Then I also mentioned about these ratios of the forces, correlation to friction. As you may know, it is being used in honing, in grinding, in turning operation, and in certain milling operations. It is also this correlation is also being used to build models, to understand machinability, and so on and so on. Especially the correlation between the feed force and cutting force. Yeah. But in our models, we often measure cutting force and we measure feed force. We divide them because that is the friction, but this is not exactly the right way. There is another procedure to make it more right, because we need to distinguish, when we look at force measurement, cutting force measurement, we need to distinguish the forces coming from the clearance side and coming from the rake side of a turning operation. And in order to do that, we need to follow a special procedure. So what can be done is that the chip thickness can be increased during turning operation. So you start with a warm-up around 10 seconds at turning operation, then you decrease your chip thickness to very low values, and then step by step increasing to high levels. Yeah. And the reason we do is that we would like to plot cutting force, so cutting force and feed force, against the chip thickness. Yeah. And when those points, this is quite linear, when they interact and intersect the y-axis here, when there is no chip thickness, you still have a force. Yeah. And those forces, as you can see here, those forces are the forces acting purely on the clearing side, as represented here, CL clearing side. So the cutting force and the feed force, they have components from the rake phase and the clearing phase. And this is a methodology to distinguish these two. Yeah. And then, of course, by using the angles on the rake and on the clearing side, you can calculate the pure friction on the rake phase of your cutting experiment. Yeah. And this, of course, can be used, as I said, to improve your models, to understand the machinability, behaviors of different materials, and also, of course, to understand the effect of any coolant or lubricants that you may have in your process. Yeah. So we talk about the dynamic part, we talk about the static part of the cutting forces, but of course, the ratio is also being, as I said, being also used in different type of operations. And this is just a methodology proposal to distinguish and use right friction coefficient. So thanks a lot for your attention, and I hope that this webinar will help you. If you have questions, you can contact your local Kistler representative in your country, or contact me also. Thanks a lot. Thank you.